Okay, so obviously this topic is like pretty huge. Um, so I'm going to kind of frame this. This is coming out of a kind of like, I would say like research sort of prototyping project that I've been doing for the past like maybe 9 months. And the kind of way I got into it, this is the kind of framing of it. I was thinking about using kind of any and all contemporary C++, like 20, 23, 26 features, and really like lean into C++ for its kind of ability to build DSLs. And I wanted to just kind of think about like, what's the sort of dream set of DSP abstractions? You know, like, what's the best possible way that we can use contemporary C++ to express kind of inner loop DSP in a really flexible way, and use it as a space to just kind of experiment and sort of imagine how we might do this. So the goals in this, part of it was I just wanted to sort of explore new C++ features, and specifically like how they might work together to kind of express really complex concepts. And I looked at kind of doing the same thing in something like Python or Rust. And I think one thing I found, there's a lot of reasons, but there's certain kinds of concepts that you can express in C++ now that are very hard to do in almost any other language. I wanted to kind of rethink the syntax, the traditional syntax and semantics of like optimized DSP code. And I wanted to just work on developing a constellation of kind of design patterns and see what happens when you put them together. And I also just wanted to make sound. Like, I'm a musician, and a primary goal of this always for me is to be able to like write code that makes cool sound. So I wanted to get not too far from that. Two inspirations for this that are in the back of my head all the time. One of them is a library called Halide, which is an image processing library. And there's a specific concept that it has, which is to separate implementation from execution. I think it's the term they use. Basically, like how to write an algorithm and then separately specify how you execute that algorithm. And that was a big, like, you'll see that running through this whole talk. The other thing that's a inspiration was this library Petra, which was just the first time I'd seen this pattern of how to hoist runtime values to compile time in a really elegant way. Basically, like, how do you take a runtime value and use it as a template parameter? And that library solved it in an interesting way that there's not a lot to it, but it's like it's something that's stuck in my head, and so you'll see that a lot in here. So we're going to look at kind of 4 things: compile time, runtime variant types, and hoisting. Constexpr directed graphs, and like how you can kind of describe graph structures at constexpr time. Flexible vectorization, and then think about how these things fit together into kind of like parametric benchmarking and optimization. I'm going to go pretty fast because there's a lot of material here. So I want to kind of touch things, sketch them out, and maybe leave them as kind of a breadcrumb trail to follow up on. I think any of these things could be, you know, a 4-hour talk just as a kind of design pattern, but I think more I want to kind of like spark some ideas. And I hope that some of these things, as you see them, it'll resonate with like maybe code that you've written and you're like, oh, this actually, I can see how this could be abstracted in an interesting way. Okay, let's go. So the first part is compile time, runtime variants, and hoisting. So what do I mean by hoisting, right? So suppose I have this like amplitude modulation function, take some inputs, I create some kind of like modulation, and then I multiply my input by that, right? So this is like, we can imagine this is doing whatever, it's doing something. So what happens if my amp is 0? Or for that matter, what happens if like frequency is audio rate modulated or just constant, right? Well, if amp is 0, then this is 0, which means this is 1. So this entire term kind of gets eliminated, right? So then this is just a pass-through of input, basically, right? So this is what I'm kind of thinking about as a problem space. So a few questions come out of this, like how can we compile different versions of amplitude modulation for each assumption, and then select the one we want? And this is kind of part of what I'm thinking about when I say hoisting. So another way to frame this is how can we pass in the concept of amp equals 1 to that function, right? How can we pass that like notion into the function? And this example is pretty trivial, but like how can we kind of generalize that? And if we generalize it, like do we get some more stuff if we start to generalize this concept of hoisting? So first, we need some kind of amp equals 1 kind of compile time constant. So let's look at how we might build this, right? So this is basically integral constant from the standard library, but like with a little more flexibility and a little more kind of embellishment. But we can go quite far with this. So if we imagine we have like a constant value type, and this is just going to take some kind of underlying type and a value parameter to its template. We just store this as a static. So this is basically a constexpr value. But we would use instances of this. We have a get function, or a method rather, that's going to return this static value. A nice thing about this is this get is constexpr. Like this is static, so we don't need to actually have any kind of runtime value at all to get this value. And then we just have a cast operator, right? To cast to the underlying type. So just with this, we can already use this constant value, like kind of anywhere we would use, if this is a float, we can kind of use it anywhere we use a float. And then maybe we make a little like, kind of value, templated value wrapper around this to make it easy to use. So this is a starting point, right, for how we would do something like this. So here's an example. Here's a 0. We pass 0 in amplitude modulation. Now when we get to this sign mod, this is a constexpr 0. So the compiler knows this is all 0. So we kind of, we're giving the compiler enough information to do quite a lot of, we can really build quite a sort of different set of code for this particular path. And of course, if we pass in like amp, some kind of runtime value, this is just straight up a different function that it calls, right? With the same expression. The code hasn't changed. It just depends on what we pass in. Okay, so there's a kind of a pleasant surprise that comes out of this too, right? This 0 value, if you have a template, value template parameter, like a double, we can pass this directly into the template, right? Because that cast operator is constexpr, and the value is just static. So when we try to cast this to double, we can do that. We don't actually need we don't actually need this to be a material sort of runtime value. So this already opens some interesting doors as far as expressiveness, because we can kind of pass these values directly into templates. We can also sort of like pass these, what would be normally template parameters, as values to arguments to a function. For symmetry, we make a runtime value type that's the same interface, but it just wraps a kind of normal runtime in an integer, float, whatever. This is just kind of to have a coherent interface. Okay, so here's a problem. I want to apply some function to my value, but I want to keep the kind of CV. I'll use CV as like kind of compile time value or constant value, and RV as runtime. So I want to kind of keep the CV RV-ness of it. So I want to like unwrap the value, apply the function, get the result, and then wrap it back up in the right format, right? So this is just an applicative. I think it's the right term. So basically what we're going to want to do with this, without kind of getting too much into the weeds here, basically we want to know if we execute that function, is it going to return us something that is like basically constexpr? And if it does, then we can wrap it up. So we apply the arguments to that function. If it's going to be constexpr, then we take this path, assign it here, and then we can kind of stick that into a CV and return it. If the result is a kind of a runtime type or just a runtime value, then we have to just wrap it in an RV and pass it back. So in this way, we can kind of have this, if we do apply with apply with func with some kind of lambda, we can kind of like unwrap. We can get this kind of unwrapping and then wrap it back up again as a CV. So we can chain these functions together and keep things constant, but we don't really care what's in the middle, right? It could also become runtime, and that's okay. So here's another problem. All my CV RV types are potentially different types, right? Like a constant value of 1 is a different type than a constant value of 10. So that means we use auto everywhere. And so how can we kind of keep some sense of like strong typing here? Well, we need to use concepts, right? So this is like a C++, I think 20 thing where you can describe constraints on a type. So we're going to make some constraints. So for example, is CV with a value type is just going to say, is this some kind of CV type that is like a float, right? Or is CV any is going to be like, is this any constant value type, right? Same with RV, right? So then our function signature starts to look like this. Rather than just auto, which is not super informative, we're going to say like, is CRV, so constant or runtime, float. So this will take any kind of float-like type, constant or runtime. So then we start to be able to build back sort of some kind of type constraints into our system without really, we still keep the flexibility of being able to pass around these constant values. Okay, what about aggregate data? So if we have a struct with some stuff in it, we can stick that struct into a CV. That's totally fine. But the problem is that this is kind of all constant or nothing, right? Like all these values are constant. But what if only frequency is constant and the amp is a runtime value? You can't really do that, right? So we could do something like this, where every field in this struct is its own kind of complicated type. And this is fine, but this is kind of a pain. This is quite verbose. And we have another problem here, which is, it's not a huge problem, but because every field has to be, you have to be able to make a pointer to it. So even if this is a constant value, which means it's sort of empty, it still has to have size 1, which is just a requirement of C++. So if you have a bunch of constant fields, you have a struct that's like a non-zero size, and that's annoying. We also kind of want parametric types, meaning that we want to be able to kind of like take a data structure and sort of mutate the types in a predictable way. It's sort of hard to do that with this, right? So I think maybe what we want here is like a property list or sort of key value pairs. That's a little more, we can kind of mess with it a little bit more. So let's call this properties, right? So this is some kind of like properties type. So I'll try to do an overview without getting into the weeds too much, but we kind of have this like 2-part structure, right? So we have an outer properties that takes a bunch of specs. So each of these specs is going to be like a type and a kind of identifier, right? So it's going to be like a float and it has this key, and that's what you'd use to access it, right? And then you have an instance, and this has the actual sort of concrete values of that, of each of those properties, right? So if this was a float, this would be like a CV float or an RV float, right? And you have to have these separated because, any number of, these could be any number of different types. Sorry. So what this looks like is from a usage perspective, like how you can use this, you would define a properties type with some fields. We'll look at those in a second, but basically like these would be a type, like a, an underlying type like float or something. You would use this kind of make factory function to make an instance of this type. And you pass in whatever the values are. If you pass in a CV, then that becomes constant, right? We're inheriting from each of those. So instance is actually just like it's derived from all of these different types. There's a little bit more wrapping here that's not shown. But this is actually how also like the standard library tuple works, right? A tuple just inherits from all of the things in the tuple, and that's how they kind of stack them up together. So for example, if you then fetch this, so you can also get these values back out by using the spec and just square brace notation. And if you get, like a CV value back out, it's still constant. So you could use this as a template parameter. When you pass it into a function, it's like the compiler knows that it's a constant value. So there's some other interesting details that come out of this, right? So you can add mix-ins to properties. I wanted to kind of show how that works, but there's just not enough time. But like this lets you kind of have sort of convenient accessor functions or sort of like algorithms that you build on top of these properties. So you're not just using this sort of obscure kind of property syntax, but you can kind of use a normal object syntax. It also helps insulate other systems. If you're like using this with another library, you can kind of just use it like normal, sort of more normal syntax. Nested properties also work, so you can have a rect that has like, let's say a size property, and that's width and height or something like that. You can also mutate property structures, which I'll show in a second. And since the constant value things are size 0 effectively, they sort of evaporate. So if you have a big property structure and it's almost all constants, those are all just sort of evaporated. So you have a nice thing where you can pass around these big structures, but actually the thing that's materially passed and on the stack is potentially much smaller. Okay, so here's a problem. Sometimes I want an array of properties, but sometimes I want a property that's a bunch of arrays. So the case that you might think of is like if you have voices, you might want one blob of property that is all the properties for each voice. But maybe you also want, if let's say the voice has a frequency property, maybe you want all the frequencies in one array, right? So how are we going to do this? Well, this is the kind of parametric data structure thing, right? So So this is, you can apply transformations to properties, right? So the way this looks, so remember we have this two-level structure. We have the description of the properties, and then we have the actual material, sort of materialization of them. So this transform takes two lambdas. The first one gives you a spec, the original spec, and lets you transform it into a new spec. You can leave it the same, or you can like design some new spec. So for example here, we take the original spec, but we wrap it, so it's like a float or something, we wrap it in an array. So the new spec is an array of whatever the thing was before, and we return this spec, right? The second lambda transforms the value, right? So now we have a new property kind of description, but we want to actually transform the value. So let's say we make a new array, we fill it with the old value is passed in, and we return that, right? So this transform now basically takes every field of that property and turns it into an array field. And the expression of this is like quite simple. And we can imagine different versions of sort of these transformations. But I think it's a really powerful concept, right? Because you no longer have to, you can have like a basic data structure that's kind of like I have these 5 fields and they're all float, and then you can describe different ways of interpreting that. So, okay, what do we have now? So we have this compile time, runtime variant type. It can be passed around as a normal value. It can also be used as a template argument if it's CV. We have structured key value pair storage. We have this kind of zero cost sort of like evaporating storage for constants. And we have a property description that you can kind of easily transform into like similar kinds of properties and do kind of really algorithmic transformations on. So this is starting to feel kind of interesting. So what do we do next with this? So the next half of this is hoisting, which is kind of where we started, right? So here's the problem space. We want to run a specific version of our process function depending on some runtime condition, right? And we do this all the time already, right? Anytime you have a branch and then you run something based on that branch, this is kind of what that is, right? For us, the idea is that we want to pull all the hoisting logic to the beginning. We pull a bunch of like decisions about what function we're going to run to the beginning, check on decide what version of the function we'll run, and then actually run it. And we want an abstraction for this too. We don't want to modify our algorithm code. So here's the kind of thing. This is like a kind of pseudocode of what we would want, right? We want to say if value is 0, then call some function with CV0. If value is 1, call it with CV1. Otherwise, just call it with a runtime value. So then we kind of have these like 2 special case versions, right? And we hopefully have picked these so that this version of the function is going to like collapse a little bit, like some part of it's going to get sort of carved off. We could also think about nesting these, right? Maybe we have a couple different values that we're, kind of selecting for. How do we implement this? I'll describe a kind of few parts of it just to get an idea. So we can describe the hoist. And we're going to do this with our property, kind of these property blobs, because it's a useful way to kind of do this, to sort of abstract this, right? So here we can describe what the hoist is that we want. So we want to hoist amp at the values of 0 and 1, right? This is what it looks like inside, which is essentially just what we saw before. So like we're passing in a bunch of the different hoist values. So we check the first one and see, okay, does the value match? If it does, then we kind of forward on to our function. There's a little bit of abstraction here, but this will basically like take that value and wrap it up in a CV and kind of forward it along. If it's not a match, if we are out of values, if we have remaining values, then we just recursively call the same thing with like the rest of the kind of hoist values. And if we run out of values, then we pass no hoist, which just basically says pass along the runtime version, right? So that's what we were doing with that little if check before. And we can do this with multiple, if you layer this up, then you can do this with multiple properties. So then the idea is, in its sort of final expression, we have some properties. We have a couple different kind of hoist descriptions. And then we do this kind of hoisted, and we give it a lambda. And this lambda is going to get called with the hoisted version of these properties, right? So hopefully, if we are hitting any of these checks, then this inputs will, instead of being called with a runtime 0, it's going to be called with a constant 0. And then this runs this amplitude modulation, and we get the kind of like optimized version of it, right? And this is a pretty clean expression of something, right? And in particular, this is not changing our actual algorithm description at all, right? We're just able to do this sort of independent of the actual content of this amplitude modulation function, right? And it falls, of course, like falls through, like if you don't hit any of the hoists, you just get the runtime values in this maybe slightly more inefficient version. So a couple other little cool details, like integer hoists can use switch, so it's like a little bit more efficient. And one thing that's really nice about this, right? So since the hoist details are just data, essentially, you can empirically test what hoist values help performance, right? So this is a way to think about, you sort of write the naive algorithm, and then you think, okay, I think actually there's a special case here, and you make a hoist for that special case, and you run it, and you can empirically test like, okay, that actually makes a huge difference, or it doesn't really matter, the compiler doesn't care, you know? And so it's a way to abstract, again, going back to that original concept, it's a way to abstract your algorithm from sort of how you run it and sort of assumptions that you put into it. Okay, so here's another problem. How do you divide up a runtime numeric range into a compile time constant chunks of work, right? So this is we've all seen this before. If you're like running, iterating over samples and you don't know how many there are, maybe you want to do loop unrolling or SIMD or whatever, right? Okay, so I'm kind of making up terms here, but maybe this will make sense. So we can do a range hoist, right? So this is we've done this before. You might work in chunks of 4, and then when you run out of chunks of 4, you kind of work in chunks of 2 or back to 1, right? Really important for SIMD because you're going to be able to operate on like vectors of 4, for example. But we want an abstraction for this because we want this independent from our algorithm. So this is what a range hoist looks like for us. We give it a couple properties. We give it a start. So given this properties blob, we give it a start value and a size. And this is just any 2 kind of property values. And it's going to basically divide up this range into whatever chunks, sort of chunk sizes that we want. And then it's going to call this lambda with with a version of that properties that represents just that chunk, right? For example, with this, it's going to call us with a start of 0, size 4, start of 4, size 4, start of 8, size 2, blah, 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 right? So what we've done here is we've taken one property of this properties, the column size, and we've turned it from a runtime value into a compile time value, right? So now we know, for example, this is always 4, so we can kind of write SIMD code around this. If we have other kinds of things that we can sort of optimize around a compile time assumption that it's like 4, units of processing. We can do that here, right? And you can do this in multiple dimensions too. If you wanted to do multiple hoist ranges, you can kind of do it, and it'll sort of basically divide it up into squares, smaller and smaller. So there's a couple other hoisting types. One thing that's kind of interesting to think about as a hoist is I'm going to call it a partitioned hoist. But basically, this is executing different parts of the graph or different graphs based on a numeric range. So the classic example of this is like an envelope. So you would execute first section of your envelope, you have one description of that curve. Next section, you have a different description of that curve, right? This is something that we use any kind of like time divided sort of breakpoint thing. You would use this abstraction. So this is a worthwhile thing also. Like I built an abstraction to this too. It's pretty easy. And then you can kind of have this concept of how do you sort of break up time into chunks. This is also really useful for values that don't change very often. So if you imagine that you have like let's say an input value that's like constant at 1, and then every once in a while it changes, like a switch that you flick, then you could do this kind of hoist where you basically say process all these samples as if this was a constant 1, and then when there's a change, process it as if it was a constant 2. So you've eliminated a branch there basically. So okay, what do we have now? I mean, it's not like writing if statements is hard. Like this is, we could write this code easily, but there's a few things that are nice about this. We can hoist branches from inner loops back to the beginning of our process call. So we basically are removing branches from inside of a loop to the beginning. So we do a bunch of branches at the beginning, and then we can call hopefully much more branch-free code. The cost is overall code size because we're increasing. We have now a bunch of kind of meta functions. But this is also parametric, right? So we can experiment with different hoisting strategies without changing our code. So we can just kind of run through different assumptions, see how they work, and see what the concrete performance is on like different systems, blah, blah, blah. Okay, so next part is graphs. Okay, so here's the kind of problem space. How do we describe the operations we're going to perform on audio, right? Our goal is to produce kind of meta functions, right? We want to have one description of what we're going to do that we can compile into different versions of and sort of transform them, tweak them algorithmically, but we want one description. I mean, writing audio DSP stuff is expensive and hard. We want to do it once and then in a clear way and then never touch it again. So directed graphs are usually the way you would represent this, and this is like the long history of audio being audio processing being represented as digraphs. So a nice thing here is that we can operate on graph structures in really predictable ways, and we can transform them and kind of know what we're going to get. It's very easy to sort of test individual pieces of the graph. It gives us a very sort of predictable way to track operations. So we're going to use this as a bridge to go between the kind of expressive version of our algorithm and a concrete, materialized, optimized version of it in a way that's kind of well-defined. And one particular thing about this is we want these graphs to be constexpr, right? We want these to be fully constant sort of compile time graphs because we want to assemble like a real function at compile time that the graph represents. Like we don't want a graph structure in memory that we're branching over, blah, blah, blah. There's like libraries to do that. We want this to turn into a simple inline function, right? Okay, so what does this look like? How will we implement this? Okay, here's a simple node. It takes some kind of value. Each node has some kind of value that it sort of wraps up, and some inputs that are other nodes. There's a bunch of different ways to represent a graph. This is a kind of simple, naive one. It works fine. So we can imagine like you have a read operation, give it a buffer, another read operation, give it another buffer, multiply operation, you give it your two inputs, right? And this is pretty straightforward. And this is like this kind of read operation. This is a kind of like template expression. Maybe this is like a little lambda that actually does the operation. Okay, so what about this though? What if we add another add here, right? And we're adding input 1, right? So now input 1 is being fed into two different nodes. We're using it twice. So there's a problem here, which is that you can't really take a reference to a constexpr value at compile time. So if we compile this is in its naive form, we're basically passing a copy of the input, right? So we have now a copy of a node. And if this node was actually a whole branch, we're basically copying the entire part of the graph. And this is obviously like not what we want. So how can we fix this? Okay, so let's instead track our nodes with like a unique ID according to their type, right? So instead of passing in the nodes themselves, we pass in just UID, like some kind of integer ID, right? This also sort of makes it easier on the compiler because instead of this like deeply nested type, this is just a value in a list of numbers, right? And then each node has its own unique ID. And we're getting this unique ID from the type itself. So it's like a unique ID corresponding to this type. So that means that another node that has the same inputs and the same operation, even if we defined it separately, has the same ID. So we get this kind of automatic deduplication happening. So if you have some kind of like, x times x and you use it 5 different times, this is going to, x times x is always going to turn into the same kind of node because it's a kind of like a content hash almost. Okay, so where does this unique ID come from, right? How do we get a unique ID from some kind of type? You can do this with friend injection. So friend injection gives us a few tricks we can use. I'm gonna not do a full rundown of this, but it's really worth you can just kind of Google this design pattern. But it gives you some tricks to handling types in a way that is very useful for what we want to build. So friend injection is going to give us basically, it's going to allow us to create a unique ID for every type in our system, so every node type. It's going to allow us to register that ID, and then later we can use that ID to retrieve the original type. So when we pass in the IDs to our node, later on, if we need to like get, okay, what actual node is this coming from? We can use that ID to look up the original type. And as long as our nodes are basically empty, like they don't have any content, they're just a compile time description, then we can always just no argument constructor, build another copy of it, right? So this allows us to kind of convert these IDs back into the original types. And this is something that's like quite hard to do otherwise. There's some other ways you can do it that are just like annoyingly sort of manual, but this makes it actually quite clean. So where does this leave us? Well, this is what our graph looks like now. So we make some nodes. The first thing is the kind of value, and then everything else is an argument, an input to that node. These are now we're just taking the ID of this and passing it in. And then at the end, we sort of compile this into a graph. This make graph, I'm not going to get into it, but that make graph, this is where we actually need to like look up the nodes in order to do like a depth first traversal and kind of turn it into a sort of more linear data structure. This is why we kind of need this ID mapping. And then we can imagine a better version of this where rather than make node, these things just look like functions, right? So, and we can like do some operator overloads. So now all of a sudden we have a multiply operator that calls, multiply op, blah, blah, blah. This is sort of pretty straightforward, but now all of a sudden our graph is starting to look kind of elegant and sort of expressive. Okay, so what can we do with the graph? So let's think about a few transformations. I want to talk about two transformations because they kind of get us, variations on these get us most of what we want. So one transformation is a map. So this is basically walk through every node, apply a function to it, and then make a new graph out of the result of that function. So you're just transforming every node into a different node. The way I implemented this, you can actually just give it any number of graphs, and you'll get each of the parallel nodes from each of those graphs. If they're the same shape, you get kind of each node from each of those graphs as your function. So you can also use it to kind of like take two graphs and combine them together. So hopefully the drawing kind of makes that clear. But this is a way to do kind of like iterative graph transformation. The shape of the graph stays the same, but you're changing what's in the node, or maybe you're injecting something to it, mutating it, whatever. Or again, a way to like combine two graphs together. Okay, the second operation is a fold. This is basically a kind of like, this is what you would think of if you're like rendering an audio graph. This is like a depth first traversal. You go to the leaves, you get the value of them, and then you pass those, like every node gets all the values of its inputs. So you can kind of just give this a lambda, and what the lambda receives is the value of that node and then the value of all of its inputs. And then you can do whatever you want with these things. Usually those nodes would have, the value would be like a lambda, like some kind of operation, but it doesn't have to be. It can be anything in there. And you can have a visitor that would kind of handle it. So like I said, these two operations and kind of variations on these get you most of what you want to do for like a simple graph stuff. I'm not going to go into all the variations. I guess I probably don't have time for it, but there's a bunch of kind of like side branches to this. So what can we do with this? Well, here's how we get external inputs, right? So we have this constexpr graph, but this has no state. It's just a kind of a description of a flow, but we want external inputs, right? So this is super simple. We have an input node that takes some kind of spec, right? And this is just like a kind of token that we would stick in our graph and kind of do something with it later. So input node, we store the spec, that's it. We can use this input node, pass it into another node. So how do we actually inflate this node with a real value? Well, we can make an input properties, and this is like one of our property blobs from before, right? So here's our inputs. And then we just do a visitor. We do a visit map, right? And we're going to go through every node in this graph, and we're going to say, is it an input node? If it is, then grab this property value and basically replace that node with the value itself. So this is actually almost identical to the code that I have in the library. Like this is all it takes, right? This visitor, you go through, you look for input nodes, you replace them with the actual value. You can imagine a bunch of other versions of this that are quite cool, right? You can imagine, for example, if you know the value of some of your nodes, you can supply the value of some of the nodes, calculate down. Maybe you can't finish calculating everything, but that's okay. You can kind of reconstruct your graph with like partial information. There's a lot of really cool things that you can do pretty simply. So how do we do stateful nodes? Right now, the nodes are kind of these empty sort of like functors or whatever, but we want state. Usually like lots of audio stuff needs state. So here's an example of how we would do state. So if we have a stateful node, it would have some kind of state struct. This describes its state. It needs an initial state before it starts. And then it has some kind of operator, right? So we can call it as a function. And this function takes the original state and its inputs. It modifies the state, calculates some value, and then returns value in a new state, right? So this is pretty simple. It's the same kind of thing we had before, but it's returning a pair. So the first thing we do is we collect all the initial states for all of our nodes. And if the state is just an empty thing, then it just kind of dissolves, right? And then every time we want to iterate the state, this visit fold stateful is kind of just a wrapper around this. We basically would call the graph with a state. This gets passed into here. And then all those states of all the nodes get collected and passed back out again. So we just kind of call this in a loop. And every time through, we get a new state. So now we have stateful nodes. Out of this kind of very simple description. A few other interesting operations we can do here. We can also do intergraph feedback. So if you have like if your graph needs one sample earlier from its own history, you can do the same thing as you're doing with inputs, but with feedback. You can also do hoisting. So you can imagine creating different transform versions of a graph based on like hoisted assumptions. Okay, so last part, trying to finish this up quickly. Vectorization. So usually SIMD vectorization in audio, most audio libraries I've seen and worked with tends to make assumptions about whether you're vectorizing along time or voices. And there's trade-offs for each of those. Some operations are faster along one axis or another. Some operations can't be vectorized along one of those axes. But usually there's a commitment to like one or the other. So time vectorization works well for like memory bound stuff because reading sequential memory is fast, buffer playback and delays and whatever. Voice vectorization is usually required when you need short time feedback like IIR filters. Certain like branching things are better with voice vectorization. All of this interacts, like how you kind of execute this interacts with the cache, CPU registers, branch prediction in pretty complex ways. And you can kind of theorize about how it interacts in small scale, but with a really, really large complex graph, the results can be surprising. So for a complex graph, this is the kind of problem space that I'm thinking of. For the complex graph, the best execution plan in vectorization is not obvious, and it can't really be determined a priori. And moreover, we don't want to have to change the description of our graph just to test a theory about, oh, there's cache misses and this is why this is slow, right? We want to be able to test theories about why something is fast or slow without actually modifying the algorithm. So the solution here is our graph describes operations on m by n vectors, so voices and time. And everything, in general, you would say only operate on voice or only operate on time. There may be cases where you'd actually want to operate in kind of a square. But generically, every operation is on some vector of m by n. And if it's m by n is 1 by 1, it's just a scalar. So this is more about how we describe the graph than it is about anything. So this is a kind of basic implementation. You can use an intrinsic vector type or something else. And then you have a block type that's basically rows and columns. And this is our abstraction for like, how many, is it voice-wise, time-wise, and how many values. So here's the problem. Blocks and SIMD vectors have compile time fixed sizes, but I want to process things with sizes that I don't know or that aren't divisible by 2 or whatever, right? So this is like, for example, buffer playback rate. If you're playing a buffer back fast, you need to read more samples, but that's a runtime value. So you kind of don't know how many samples to read. It's quite hard to do that with SIMD, right? Num samples shouldn't change between calls, but like a lot of, like most sort of audio hosts have an assumption that the num samples is kind of a runtime property, right? Wavetables, you might have different wavetable sizes and you don't know what the size is, right? So we already have a solution to this problem, right? This is a range hoist. So because range hoist that we looked at earlier is a way of breaking up a range that is a runtime value into compile time chunks, right? So we can just use a range hoist to take any kind of operation of any size and break it up into sort of SIMD chunks. So this is where it kind of interacts with this storage structure in a really nice way. Okay, so the last problem here, my graph is really complex and I just have no idea what execution plan is more efficient. Maybe I make some assumptions, but like whatever. I'm reading from 8 buffers, then I'm also processing them with filters. So like buffers should be read time parallel, maybe, but then the IRs have to be voice parallel, and like what's the trade-off? How much is the cache hurting me here? So the real solution to this is to just parameterize it and test. But what we've been kind of working toward all along is that all of these ways of breaking up your, like how you call the function, how you execute it, what chunks you're using, what your execution plan is, this is all parameterized separate from the graph description itself. So you can just try different execution plans and see which one actually works better on different platforms, by voice, by time. You can even break your graph up into subsections and say, okay, well, this part of the graph, I need to actually read a bunch of stuff in over time, but then the rest of it needs to be by voice. And so you can kind of do subgraphs and figure out like empirically which one works better. So like just as an example, this is basic linear interpolation. And this I implemented kind of purely through the framework with no kind of handoff. It doesn't touch, I mean, it's using SIMD, but I'm not touching any SIMD stuff. It's just kind of naively doing it with the kind of graph description that I built. And then I'm just trying out different execution plans, right? So just really simply like the naive scalar version, this is just like a for loop version. So we can see like the 1 by 2, so like 2 is 2 samples at a time. We get a kind of 2x speed up, which makes sense. If we're SIMD executing the same thing, then it makes sense that we're gonna kind of have half as many operations. It's like in the ballpark. But we also see some different, like, we see some small differences between different execution plans. And, we could then kind of go back and look at like, what's the code gen for this? Why is maybe one of, the code gen for one of these things faster? We could do some profiling and look at like, okay, are there like, are there cache factors that are coming in to make this slower or faster? But this gives us the ability to really like empirically kind of like test every possible combination, try out what works, and then move forward with it from there. So what do we have now? We have a way of describing operations on audio that's independent of how we process it. We have a building block to build a library of kind of fast vector operations, this kind of block concept. And we have the ability to execute or experiment with different execution plans to test performance, and we don't change code, right? We're not changing any algorithm, we're just changing how we execute it. So one thing that's also kind of interesting about this is, as if we go further with this, it starts to look like all of these different kinds of processing begin to collapse, right? So like wavetable synthesis, additive synthesis, granular, wave terrain, blah, 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 are almost identical. They're all just like different ways of reading buffers in different combinations. And so we start to see actually that maybe we can kind of build a sort of meta, like a few kind of meta functions for this that would actually describe like a huge sort of territory of different kinds of audio operations that we want. So what's next for me on this? I'll end this really quick. I'm gonna keep working on this library. It's quite a prototype, so I think there's gonna be a space, once I kind of get a couple demos done with it, I wanna go back and kind of extract things and sort of rewrite it, because it's been a play space for me, and it's been a space to kind of test theories. But I think I have found that some of these concepts, when you put them together, are very expressive. Cool. Thanks. If you follow that GitHub, you can track me there, and I'll also be posting project updates, and I'll post the code later today along with the slides.
Brilliant. Thank you. Round of applause to Scott.